Assalamu alaikum, dear students. Uh, Today we are going to discuss micrometer screw gauge, another device that you have been using in O levels, and you have fairly good idea what it looks like. Exactly how we take reading with this is similar to what we did yesterday, with a few differences that we are going to discuss now, because there are questions in the exam, and you will be using this device very frequently in the lab. Hopefully when you start coming, maybe in September, then we'll regularly go to the lab and you will be using measurements with the help of micrometer screw gauge. It looks like a U-shaped part, and this is a fixed part, and one screw type object, a cylinder that moves outward when you turn this part, which is the circular scale. And you place an object here, and suppose this is the diameter of this spherical ball is to be determined. I hope you know that when we hold it inside here, it is with the help of this screw that we tighten these screws, so it's not too much of force that we apply on it. So due to the gentle force required here, instead of pushing this with the help of this thimble, we use this screw to tighten this further. And when we are sure this is in place, then we take the reading of this main scale. So like we did in the vernier caliper, the first thing we notice is the main scale reading. Main scale reading means this is the scale, which is a millimeter scale, and we have markings on it starting from 0 here. We have 1 millimeter, this is 2 millimeter, this is 3 millimeter, this is 4, and this is 5. So we have 5 written here because this is a millimeter scale. So that means 1, 2, 3, 4, and 5 millimeter, then 6, 7, 8, 9, and 10 millimeter. And similarly, 1, 2, 3, and 4. If you look at this carefully, this fourth division after this 10, if I count, this is 11, 12, 13, 14. So this is 14 millimeter is our main scale reading, because this time 14th division is that mark which has just been passed by this circular scale. This is the line that tells us what should be the main scale reading. If this line just passes by a mark, but it has not crossed the next one, obviously 14th is just visible, so 15th is behind it. So our reading is 14 millimeter. You will not take it 14.5 or 14.25. You will only take the main scale reading as that division which is just crossed by this line. Then the next thing is similar to what we did in the case of micrometers in the vernier caliper, the coinciding vernier scale division there, and now we'll call it coinciding circular scale division. So we have a different name here, otherwise it is the same N. So this time we'll look at what is the circular scale division, which exactly coincides with this line. This is the line that will show a certain circular scale division coinciding with it. So we have a circular scale on it, and on circular scale we have exactly 50 divisions, and 50 divisions start from 0, and as we move it in the anti-clockwise sense, like this, we open it like any screw is opened. This scale moves towards the right, and this scale becomes more and more visible. The circular scale on it has 50 division on it, and when I fully close this, 0 is exactly comes here. So obviously when I have opened it, 0 moves in this manner. It goes down first, then it makes a round trip and then comes back, making half a millimeter division on it. We have these marks as well, which means after each division we have the possibility of measuring half a millimeter on the main scale as well. So these half divisions are also a part of this main scale reading. So each complete round trip of this circular scale means half a millimeter movement on this scale. That is known as the pitch of the scale, but that definition is not required in your syllabus. So naturally, when I have started opening this, moving it in this manner, 0 goes down somewhere, and it is expected that we have a division here, something like 20 maybe, or 21 or 22. So we have a division which is clearly visible here, or the nearest one. So this is always rounded off to the nearest division that we find exactly coinciding with this line. Let's say this is 22nd division that we find coinciding with this. So in this case it is 22. This 22 is multiplied by the least count, and this number which is written on this device is 0.01 millimeter. So if I multiply this by this number, the total value, which means the diameter of the sphere, our measurement is 14 plus 0.01 times 22. So I think this will be 14.22 millimeter diameter of this device. I quickly repeat what we have done. The first thing is to carefully place this object here and hold it firmly with the help of this part. This is a screw at the end of the micrometer screw gauge, just to make sure it is not too much of the force applied on it. So it is gently and firmly held in this position, and we can take it out carefully if it's easy. And then we take the main scale reading. Main scale reading is that last visible part of this scale. The last division visible here is 14 millimeter. If I move it slightly to this side, maybe 14.5, the next division below this scale will become visible. In that case, it would be 14.5. But since that division is not visible, so 14 millimeter is our main scale reading. And then we see which division on the circular scale, which has so many divisions like this, and they are 50 in all. So we can clearly count them, and if I find that it is 22nd division coinciding with the line, this line, then 22nd is multiplied by the least count, which is written on the device 0.01. Even if you don't remember it, you can check it from the micrometer you are using, and then you use this simple formula to calculate the diameters. This is how we use micrometer screw gauge. A more important thing that we can discuss now is the CRO, the cathode ray oscilloscope, because the other scales are more familiar ones, easy one. For example, protractor, the thermometer scale, the scale on the Newton meter. You will observe all these things in the lab when you start coming to the school, and that will be easy, and you have already observed them. So I'm not concerned about that part so much, but CRO is that part which needs to be discussed in sufficient detail, so you know how to interpret what we see on the screen. This is the CRO screen, and the question in the exam are always about what we see on the screen, and it's not about what is behind the screen. It's not about the electron gun anymore. It's not about the X and Y plates and how they are arranged and what is the screen is made of. So these are the questions we used to have in O levels, but in A level we always have questions which require you to interpret the trace that you see on the screen. A screen looks like this, with a grid shown. Each box is exactly 1 centimeter wide and 1 centimeter long. So that means exactly 1 centimeter across. So this is the screen. Similarly, we have so this is the grid provided, and on this grid you will have various traces, and each trace will have its own unique frequency and time period. So let's say this is the screen provided. This is always the axis. Usually the trace is symmetric about these two axes. They have not labeled these axes, and you are not required to label these axes as well. You just have to interpret the trace. The simplest one could be something like this. This is a simple trace on the CRO screen. The CRO screen is a device which is connected to any source, which could be a source of sound, which could be a source where pressure is varying, but whatever that quantity is, that is converted by this device into voltages first, and then these voltages are shown varying in this manner. So it is the voltage across this axis. We can say this is y-axis, and this x-axis is actually the time-based setting, and both settings affect the shape of this graph. Two things that are part of this device, and that is usually given. One of them is the time-based setting, time-based setting, and the other is we have a knob here where we can make that setting, and one is Y gain setting. Y gain setting is also a knob with different options. We have various options to make this setting. Usually for time-based setting, time-based setting usually have a few options, and typically they range between 5 millivolt millisecond per centimeter to 25 millisecond per centimeter. So we have time-based setting in this range. Suppose I select a value of 10 millisecond per centimeter, and I label this value as small t. And this is the shape of the graph I have on the screen. This setting is our choice, and we can make this setting with the help of a knob on the device. And with this choice, 10 millisecond per centimeter, we have this shape of the graph, and we want to know what is the time period and frequency of this signal. Time period is calculated using a simple formula in which a number, which is determined from the screen, and I'm coming to that, what it means. This number is multiplied by this t, the time-based setting. So this formula becomes capital T is equal to n times small t. This is the time period of this trace. This is the time-based setting of the device, which I said is our choice. And this capital T is the characteristic of this trace. I cannot change this because this is something to do with the original signal. If it's a voltage signal attached to the device, its value of T will remain the same, whatever our setting happen to be. But what is this N? This N is the total number of boxes in which a complete wave of this trace fits. And they are 4 in number, 1, 2, 3, and 4. As you see, this whole wave completes in 4 boxes. And then it repeats itself in another 4 boxes, and then it continues. So if it is clearly seen that a certain wave is fitting in certain number of boxes along x-axis, because this is the time-based setting along x-axis, so boxes are count along this and not along this. So along x-axis, when I count, n is 4, and when I multiply this 4, because this 4 is centimeter, so let's say this is centimeter into T, which is 10 millisecond per centimeter, and I wrote these units because I wanted to show that this centimeter gets cancelled with this centimeter, and we are left with 40 milliseconds. So 40 millisecond is the period of this wave. This simple trace is taking 40 millisecond to complete itself. So 40 millisecond, its time period. What is the frequency? Obviously, that is very easy now. Frequency is simply 1 over t. So 1 over 40 into 10 raised power minus 3. Do not forget this part, 10 raised power minus 3, because this is not 1 over 40. This is 40 milliseconds. So 10 raised power minus 3 should be a part of it. So this is 1000 divided by 40. So you can simplify it and see what it comes out to be. A few hundred hertz is the frequency, because you know the time period and you know the frequency, you know this trace now. But what if we change the setting? It is possible to change the setting to, suppose instead of 10 millisecond, you make another choice from this available options. You make it 20. So T is equal to N into T. Now this value is changed to 20 millisecond per centimeter. So I keep it 20. Instead of writing units with it, I keep it 20 now. And my the purpose of changing the setting is to show what happens to the shape of the graph, and that is something, the change that will take place is the number of boxes in which the wave will fit in. So you will be either having fewer waves on the screen or larger waves on the screen. That is something we are going to see now. What about this T? Let me emphasize it here, and you will remember always that by changing this setting, I am not changing the time period of this signal at all, because the signal has its unique value of time period and frequency, and whatever setting I have in the beginning and whatever value I have calculated using that setting remains the same, because time period of a wave or frequency of a wave does not change as long as we change the source or the signal itself, and that we are not doing. We are only changing the setting of this device, and I'm changing this setting from 10 to 20, and as a result this N will change, and as a result the way the trace looks on the screen will be different. And this capital T, as I said, should be same as 40 millisecond. Since we have millisecond on this side and millisecond on this side, so I've not written it. But as you see clearly, N is 40 over 20, so it is 2 now. So what do you expect will be the shape of the trace now? The shape of the trace will be very different, because N is 2, which means the complete wave will fit in only 2 boxes now. So you have larger waves visible on the screen. That means a trace like this will be visible. So you have many waves. So instead of 1 wave in 4 boxes, we have 2 waves in 4 boxes. That means 1 wave will fit in only 2 boxes now. So a wave of this shape will be visible on it. So this is how the trace will look like. This. If I erase this, so this is how the shape of the graph will change. So what has happened? We have changed the time-based setting. We have increased it from 10 millisecond per centimeter to 20 millisecond per centimeter, and we have seen that the wave is squeezed a bit, and we have a larger number of waves appearing on the screen. But that doesn't mean that I have increased the frequency of the wave, or I have decreased the time period. We have just changed the appearance of the wave. The way it looks on the screen is different. I'm emphasizing this point again and again because students confuse this change with the change in frequency or the time period, and that is not the case. We have not made any change in the Y gain setting, so its height will remain unchanged. It is the same amplitude, the same, but that part I'll discuss tomorrow because I don't want the two things to mix up. What we have discussed today is only what happens to the appearance of the wave when we change the time-based setting. So time-based setting, we have a few options, and I have tried a couple of options and see what is the typical change in the way the trace looks like. So I stop here, and the remaining part of it will be discussed tomorrow with the change in the time base, the Y gain setting, and then we'll have a few questions for practice. Thank you for today.